So we're just gonna start. A lot of people are still kind of late, including Miss Silcock, but we don't have too much time, so it would just be unfortunate for them. So today we're gonna be going over introduction to machine learning and artificial intelligence, right? ML and AI, just abbreviations. More specifically, today we're gonna spend most of time talking about introduction to machine learning and mainly image classification in machine learning. Um, but first, we do have like a schedule change or like a schedule announcement, and that is that our last meeting is gonna be on April 13th. So, on par with like most high school clubs end around middle of April to give people time to study for like AP tests, finals, and etc. And so we're gonna be doing the same. Obviously, all of you probably don't have AP tests or like as many finals and such, but we're just going to be ending on April 13th as our last meeting, nevertheless. There would have only been two other meetings, anyways, so it's not too much of a loss. The next two meetings will be both going over machine learning and AI. And so these are like table of content structure that we're going over today. So first we're going to talk about some common examples. Then we're going to talk about like the differences between ML versus AI. And then we're going to go over terminology, then image classification, and then we'll go over CNN if we have time. And lastly, we'll have a short demo at the end. So first, this is like little word cloud that I found the other day. But basically, these are like things that are related to machine learning and AI and stuff that like sectors and industries that can be applied to it. In short, basically almost every like job type sector can be improved, can be like replaced with machines and artificial intelligence. And yeah, it's kind of scary, but that's a whole different conversation. But some common examples you might be seeing are like recommendation algorithms. So that's like, for example, on YouTube, if like you're looking at your recommendations, right, your feed on social media, it's nonstop personalized feed. On Netflix, the shows you're looking at, they're all personalized. Search engine algorithms, those are very similar, except it's like, when you're searching. So like when you're using Google to search, like maybe the results are filtered a bit so it matches more to what you like or matches more to your demographic or your location, whatever. And then GPS/navigation, that one's kind of self-explanatory. How like Google Maps finds the best route, face recognition, self-driving cars, and then tagged photos. By tagged photos, what we mean is basically nowadays, you guys might know, but when you take like pictures and it's like in your camera roll, they like can get categorized for you, even though you don't have to do any categorizing. So like, if I like take a picture of like a dog and I just save it, later on, my phone knows that hey, this is a picture of a dog, right? Even though I never told it that it's a dog. And then I could search through my photos and I could type in dog and that picture will pop up, even though I never specifically labeled that this is a dog. And we'll be talking about that a lot more because that's the main like topic for today's lesson. And then so the differences between machine learning and artificial intelligence, this is kind of short, but they have the two terms have been commonly like interchanged and misused a lot because they're both like buzzwords and kind of very big. But in a nutshell, machine learning is a branch of AI. And then um that's new. And then, so in short, machine learning is a study of computer algorithms that allow computer programs to automatically improve through experience. And this is from CMU, Carnegie Mellon University. They're like a top five computer science university. And in short, basically algorithms that can learn from data. That's basically what machine learning is. The main part is that they learn from data. And artificial intelligence is a bit different. It's the science and engineering of making computers believe in ways that until recently we thought required human intelligence, also from CMU. Basically, artificial intelligence is software that can like solve problems by itself. And those are the two main differences. And now we're gonna look at some like we're gonna look at quick draw. Basically, this is quick draw. It's pretty interesting. Um, it is a game built with machine learning, just by Google. Um, Everything that says like with google.com, that's Google's secondary server. So it's like all of Google's like projects and experiments and stuff, and they have a lot of them. But basically, you draw, and a neural network trains to guess what you're drawing. It doesn't always work, but the more you play with it, the more it will learn. So far, we have trained it on a few hundred concepts, and we hope to add more over time. Blah blah blah. So we're gonna quickly demo it. So click let's draw, and we have to draw a flashlight under 20 seconds. And supposedly, this computer, this neural network, this machine is supposed to be able to recognize what I'm drawing. So my drawing skills aren't that good, but I think we can draw a
I
flashlight.
see line, or bread, or skyscraper, or stethoscope. I see pants,
Okay, it's a
or vase,
flashlight.
or toothpaste.
Bruh.
Oh, I know, it's
It
flashlight.
works. See, that was a flashlight. And we'll draw a hammer.
I see line,
Getting kind of
or
nervous.
toothbrush, or string bean, or marker. I see spoon, or crayon.
Unfortunate. Okay, so I guess those my drawing skills.
Sorry, I couldn't guess it.
Alright, so we'll draw a saw.
I see leg, or square, or book, or eraser, or anvil. Oh, I know, it's saw.
So we got three more. This will be fast. Let's
I
see.
see line, or underwear.
Diamond.
I see parachute. Oh, I know, it's diamond.
Bulldozer.
I see circle, or blueberry, or tractor, or binoculars.
There's a
Oh, I
bulldozer,
know,
right?
it's bulldozer.
So last one, we'll draw a leg.
I see knee. Oh, I know, it's leg.
All right, so basically we're done. It recognized 5 out of 6 that we drew, which is pretty cool. I guess my hammer's just bad. But and then you can click on it and you can see what it thought it was. So it thought it was a marker. I don't see it, but apparently the machine thought it was a marker, and it also thought it was a toothbrush or a spoon. I don't know about you, but that looks like a hammer to me. And I guess these are better images of hammers. And so those are like other people's drawings. And so there's two things that are important. The first thing is that Google is really smart because one, this is a game, and two, they have so much data. So look at all of these images, right? And if you click on any one, like a postcard, for example, we're looking at over 100,000 different drawings by people of postcards. And all of this is like real, like valid and good data that machines can later train on. So that's pretty cool. And then also we're we're gonna quickly go and check out Teachable Machine. It's also by Google. Basically, can teach it to do stuff and teach it to train to recognize different things. So we're gonna train it to recognize images. We're gonna try to do this fast. Heads up, I need to turn off my camera because otherwise it won't be able to see me in Chrome. But you guys should be able to still like see me when I turn on. All right, so basically, um, right, so you can see, right? I need to stand out of the view. What we're gonna do is basically we're gonna train the model to recognize a solved Rubik's cube versus like a scrambled Rubik's cube. So I have two cubes right here. This one's solved, and so we're gonna train it to recognize like this image. So basically, right now all I'm doing is holding and recording different samples, and then twisting the cube so like you gets different images. Um, Heads up, I don't know if I said this yet, but I tried it 4 times in preparation, and only 2 out of 4 times worked, so it might not work. And then we'll add a sample, and this one will kind of scramble the cube a bit. So you see this like kind of scrambled, and we'll try to do the exact same thing. So it's not perfect, and the reason why it's not perfect is because um, there are a lot of different factors like the lighting, like my face is in there, so like if my face changes expression too, all of that stuff. But it's decently accurate, and then after it trains, which shouldn't take, oh, what? Oh, it's working though. Right, it says training, right? Yeah, it's training. Okay, that was weird. But after it trains, which is pretty quick, we should be able to, like show it a scrambled or solved cube, and it should be able to tell me if it's class one or class two, right? Class one is it solved, class two is it scrambled. Though once again, heads up, it's likely it won't work, which will be unfortunate. So I've shown the scrambled cube, show still just class two, right? And if I show a solved cube, it should uh okay, I don't think it's working. Well, in theory, it was supposed to show that it was supposed to show that it was a solved cube in class one, but I guess other factors went to play. Normally, like normally you would have like better data, like not me like twisting the cube a bunch, like my hands were rotating it. But yeah, anyways, that's that. So now let's speed through the rest of the lesson. Um, that took a bit longer than I thought. But now machine learning terminology. So this stuff is a bit advanced. So if you're like falling behind, like raise your hand or message me in the chat and I'll like slow down. But first is labels. So label is a trait that we want to predict. So we're going to be using the example of emails. So the label that we want to predict is if an email is spam or not spam, right? Spam is the first label, not spam is the second label. And then we have features. Features are input variables. So a simple project might only use one feature, while like a more advanced one might use like millions of features. In our example, we're going to be using four features: words in email text, the sender's address, the time of the email, and then whether the email contains the phrase one weird trick. So you can think of them kind of like as just variables, right? And they might hold like a weight from 0 to 1, etc., right? Or whatever. You can think of them however you want to think of them. But basically, these are your features, and we grab these features, and then given the features, we determine if the label is spam or not spam. So for example, right, if the email contains the phrase one weird trick, that might be like a red flag to us, and we might mark it as spam. But basically, that's how features work. And then examples. So an example is an instance of data. There are two types of examples. The first one is labeled examples. They include both the feature and the label, and they're used to train the model. So an example of a labeled example is emails that the user has explicitly marked as spam or not spam. So if I, the user, got an email and I marked it as spam, that would be a labeled example, right? Because then the machine can go and take that email and train on it because it knows that, hey, this is a spam email. So this email has features XYZ, right? Whatever, ABCD, right? And then given that the fact that this email has ABCD features, this one's spam. So it learns from that. And then unlabeled examples are the opposite. So it contains the features ABCD, but it doesn't contain the label. And we use the model to predict the label on unlabeled examples. So for example, if a new email has been in my inbox and I haven't labeled it as spam or not spam yet, then the machine tries to label it using its model, right? So the machine tries to label it and it tries to label it as spam or not spam. And that's how you test the machine basically. That one's training, and this is like more in development when it's working. So last thing on this slide is all of your machines, all of your models, you're gonna first train them and then you're gonna test them. And then last thing is a model. So a model is the algorithm that defines the relationship between features and labels. So in our model defines the relationship between the features, right, which we mentioned here, right, all of these things here, and the relationship between these four things and these two things, right? So relationship between A, B, C, D versus spam and not spam, and that's our model. And the two phases, right? The first one is training. That's where we're creating it. We're showing the model labeled examples, and we're letting it gradually learn. And then the second phase is inference, which is when we're actually applying it and we're trying to, make it guess the labels on unlabeled examples. And that's like more in production. And so that's all for machine learning terminology. That also is roughly how machine learning works. You have examples, you train the model on examples, and then you test the model on unlabeled examples. If you have any questions, now is the time. Otherwise, we're going to be talking about image classification. These slides are from Stanford's CS213N course. It's a computer vision course from 2017. It's like a really, really good course, and it's all on like YouTube. The slides are all posted and everything. I didn't think I was gonna be able to create like a better slideshow than theirs, so I just literally copy and pasted it. Um, so to start, if we want to classify images, what we're given, our input is going to be a picture, right? In our case, it's a cat. And then given this cat, we have to, you know, assume that, hey, we have to figure out that this image references a cat, right? From a set of discrete labels. You can ignore this if you don't know what a set is or discrete labels or anything. But basically, we're given an image, we want to label it as a cat. And there are a couple of challenges. And the challenges, we call them the semantic gap. Semantic just means like related to processing images. You can ignore it. Um, but the first thing is that what does the computer see, right? With our eyes, we can see an actual image, but computer can't see like an image like that. Instead, all it sees is a bunch of pixels, right? Because that's what an image boils down to, a bunch of pixels. And what a pixel is, right? A pixel boils down to three colors, red, green, blue, right? RGB values. And RGB values range from 0 to 255. So that's why what it sees is a bunch of data. And you can think of the data in three channels, right? And the dimensions for these channels are 800 by 600 by 3. 800 by 600 are the dimensions of your image. So our image here is 800 by 600 pixels long and wide, right? And then 3 is always going to be 3 because there are only three colors, red, green, blue. And so that's what the computer sees, a bunch of pixels in red, green, blue values. And the first like actual challenge is viewpoint variation. So if our camera was originally from here, taking the picture like this, but then if we rotate it like 180 degrees, it's gonna show a whole different picture with whole different values, right? All of your pixels are gonna get modified. They're gonna be different, except it's still a cat. So you still have to figure out how to accommodate for that. Even though all your pixels are changed, it's like a whole different image, it's still a cat. And then illumination, same concept, right? In different lighting, the cat might look different and the image might look different and the pixels might look different. Deformation, there are different types of cat. Some of them are sitting weird, some of them are deformed, quote unquote, right? And so once again, you have to recognize that it's still a cat. Occlusion, if it's hiding behind something. So this one's under a blanket, this one's in a bush, this one's underneath a couch where you can only see like a little tail and a hump. Right? So all of these are going to be very like different and hard to differentiate when you're just looking at pixels. Background color, these two cats are blending in with their respective backgrounds. Intra-class variation, so basically baby cats, kittens, right? And you know there are different breeds of cats, I assume. And so we still have to be able to recognize that all in all, we want to recognize this image as a cat. And so those are all of our challenges. So now if you want to try and write an image classifier, you might try and write a function, right? So our function might be classify image. And in the parameter or the input that we're taking is the image. Then we do some magic and we return the class label. In our case, we want to return a cat if the image is a cat. And so there is no obvious way to do the magic so and so because like unlike sorting a list of numbers where you can like hard code it, there is a obvious way to hard code that algorithm. There is no way to hard code recognizing a cat or other classes. There have been many attempts made. So this one's pretty actually smart. It finds the edges. So it does some edge detection, turns it black and white. So you can see all these edges here, right? And then given the edges, it finds the corners. And then it does some rules. So for example, the first rule might be a cat has 2 ears. So if you ever see three lines going to one corner and you see that twice, right, that might mean it's two different ears. And then it might have a tail, right? And it might have paws, whatever. And so it has a bunch of rules. And then given these rules, if they all are matched, if they all are checked, then you might output, hey, this is a cat. And there's two problems with it. The first is obvious, is it isn't like going to work for everything. There are going to be edge cases where it doesn't look like a cat via the edges, but we can still tell it's a cat. And the second problem, which is the bigger problem, is that it's hard to scale up. So if you think about it, if I want to recognize a dog, I don't know how to recognize a dog with the current algorithm I have. I would have to rewrite my algorithm to recognize a dog. This time, looking at features of a dog that are different than a cat. And so it's unscalable. And so basically, yeah, I think we have enough time. We'll just quickly watch this video. It's 3 minutes. It explains CNN and how we can classify images.
The internet wouldn't be the same without cats. From Garfield to Lil Bub and GitHub's Octocat, cats have become the internet's unofficial mascot, playing critical roles in some of the web's most viral content. But cats are unpredictable creatures. With millions upon millions of cat photos on the web, each containing very different shapes, textures, colors, poses, and backgrounds, how do we determine whether an image has a cat in it? Google Photos organizes all of your photos and makes them searchable. But how are cat photos identified when they are merely labeled with nondescript terms like Max? Image classification assigns text labels to images. But even with a huge number of training examples, computers cannot extrapolate enough meaningful information from raw pixels alone to easily identify a cat in a photo. We need to build models that can see pictures more like humans do. We can do that with a convolutional neural network. A convolutional filter is an n by n, for example, 3 by 3 grid of numbers that is applied to an image in different ways to generate a feature map, a map of all feature crosses or combinations in the image. Filters form a feature hierarchy. ConvNets use filters to build representations that become progressively easier to classify. From pixels to textures, from textures to shapes, and from shapes to objects. Training a small ConvNet, we can build a cat classifier that can identify cats with up to 80% accuracy using just 40 lines of code. Let's see the image classifier in action. Is there a cat in this photo? Definitely. How about this one? Most certainly not. A drawing of a cat is still identified as a cat. So is a cat relaxing on a bed. But a cat in a bunny-shaped cat bed? Not so much. However, even despite its high accuracy, the ConvNet has its limitations. As you can see, the human eye is still better than a machine at cat classification. Using a similar technique to the cat classifier, we can train models to classify dogs or even inanimate objects like handbags. To identify content labels in our training data, we leverage the same Google machine learning technology that powers Google Image Search and Google Photos, which can recognize over 27,000 different labels. ConvNets can also be trained to recognize more abstract concepts, such as whether a photo was taken on a smartphone or by a professional. These nets can be built on top of a pre-trained based network via a process called transfer learning, which makes it possible.
Yeah, so I'm gonna pause it there. Basically, that's it. We're not gonna be like talking about transfer learning. So, just quickly before I hand it off to Zenkai for the demo, the most important thing that you should like hopefully have taken away from like the past 25 however many minutes is that in machine learning is built off data, and that's why data is so important. You probably hear all day like, people are worried about their data, they want to secure your data, blah blah blah. Companies want to sell your data, etc., because data is very powerful. And in machine learning and machine specifically, your models are trained off data, right? So like with the quick draw we saw earlier, Google has like 100,000s of photos for each of those little objects in your like little game. And the last scene is the convolutional neural network, or CNN for short. And that's like how we truly can classify images, because pixels and pixels alone don't work because of the semantic gap that we showed a bit earlier. So now I'm going to stop sharing, and Zenkai is going to go over a quick demo, I think.
Give me a second. Let's see. Okay. So yeah, today so I'm going to be doing a demo using Keras, which is which belongs to TensorFlow, which is a machine learning framework. Basically, we're going to use the CNN we just learned about to recognize handwritten digits. Okay, this is a classical classical example of how machine learning can be used. And so not so frequently asked questions. So what is TensorFlow/Keras? So TensorFlow is a machine learning framework. If you don't understand that, don't worry about it. It's not that important anyway. Keras is basically TensorFlow, but simplified, and you can access it. So if you're using Python, you can access it using TensorFlow.keras. So question 2, will I understand everything here? Okay, it'll be nicer you do, but it's normal if you don't, because you haven't learned calculus yet. So there's no way we're going to be able to like explain everything theoretical to you. So yeah, we won't be covering the math because you haven't learned it yet. And something about the machine learning stuff might not make sense without math, but it's probably all right because it should make sense intuitively, even though you don't understand how it works underneath the hood. So how does this thing work roughly? So we have Keras, which is TensorFlow, and we feed it with some training data, and the model is and the algorithm makes the model with the training data and profit. Yeah. So question 4, what can we do with machine learning? Okay, as this slide has said, you can do a bunch of stuff, but here I'm just gonna have some more examples. So of course, image recognition. So this is what we're doing today. We can do audio recognition. So that's basically, Siri, Google Assistant, something like that. You can also do natural language processing, NLP. This has other applications. Okay, not really sure any concrete ones. But I did learn about like some lawyers can like use NLP to like analyze all the documents, thousands of documents they've received, and find out which one's useful. So yeah, YouTube probably uses machine learning to analyze their videos and demonetize them, obviously. And you can use GAN to make weird art. Of course, there's more to it than that, but you can also use machine learning to like help with translating. Yeah, Google Translate is already using that. So there are a ton of basically a ton of applications of machine learning in the real world. So today we'll be using the convolutional neural network, aka CNN or ConvNet. And so this is basically how it works. Okay, you have an input image, which is a handwritten digit that is so the drawn parts are black or gray, and the background is white, and basically a grayscale image. So that's which is easier for the algorithm to like kind of detect, I guess. And you give it to the algorithm, and or more to be more precise, you give it to the model. The model makes a prediction, and yeah, this is the entire model. Okay, and these are the layers, and it passes through each of the layers, and finally it gives you like 10 possibilities, and each so they're the possibilities of whether the image belongs to a certain class. So the highest one, meaning the highest one represents the correct label for this image. So if there's a 2, then this node should have the highest possibility, the highest probability. Yeah. Don't worry about what these layers are, okay, because it's pretty complicated. And yeah, chances are you haven't seen this thing before. So this is Google Colab. Okay, Google Colab, and it's an online platform for running Jupyter notebooks. And what is Jupyter notebook? Okay, it's basically a kind of a well, it's a digital notebook that helps you visualize I guess visualize concepts and explain stuff, and add code to it, and you can run code in this notebook as well. So it's kind of helpful. So if you develop some kind of algorithm and you share with others, Jupyter Notebook can help you explain it to the people you share it with. So yeah. it's pretty widely used in machine learning and this kind of field. Don't worry about this. Since you're running it on Google Colab, you don't have to install anything locally. Of course, if you have a very powerful GPU, or if if you use like AWS or DigitalOcean, you can of course install it there, but not sure if you don't worry about it. So here is the actual code. Okay, we start by importing a bunch of machine learning packages or libraries. So NumPy is used for scientific calculations like arrays, matrices, and a bunch of other manipulation of those data structures. TensorFlow is the machine learning framework we talked about, and Keras is the simplified version of TensorFlow. Matplotlib, this is pretty self-explanatory. It's a library for plotting stuff. Okay, let's run this. And it's going to connect to Google and allocate some kind of computer for us to run this thing. And now this has been ran, I assume. Yeah. So after setting up the libraries, we prepare the data. So normally, of course, in the real life, you have to find and prepare your own data. But in this case, we already have the data from Keras. So this data set is called MNIST. You can get it from Keras directly, and you can split it into the training data set and the testing data set. So the training data set is what is used during the training process, and the testing data set is used to evaluate its performance, basically. So that the training algorithm knows how well it's doing. Don't worry about this. This is just to like make the data more suitable for the training algorithm, I guess. Yeah, this too. This converts the numerical label 0 to 9 to a kind of a matrix or a vector. So so if you use like a numerical label of 0 to 9, the machine it's easy for the machine learning algorithm to mistake it for like a kind of a regression. So yeah, don't worry about it. Let's just run it. Yeah. 0 microsecond per step. Okay. Okay. Sus. Fire range plugins. I don't know, was it not downloaded properly? Dude. Okay. Bro, it worked last time I used it though. Okay, so this step is supposed to show the data set, but something is kind of wrong. And just imagine here, imagine there are 9 images of handwritten digits, and each of them has a label 0 to 9, basically. And yeah, the label combined with the image is an example within the data set. So the algorithm trains on these examples. So now we have the data, we have split it into like training and testing data set, and we can use it to, we can first build a model. So Keras made it like really simple to build a model. So we basically have a bunch of layers. So convolution layers, max pooling layers, and you flatten it, and you this is a neural net. Don't worry about it. This is just the layers I've shown you in the picture from earlier. Each of them is a layer, basically. So yeah, model.summary prints like a kind of a table of how the model is supposed to work. Now we can train the data. So you have to compile the model and specify what kind of loss function it has. So a loss function basically determines how well the model is working. And the optimizer, well, it's probably self-explanatory. It optimizes the learning algorithm. No, it optimizes the learning process. And the metrics is just what it shows when it's training. So accuracy. And this is probably going to take some time since we have 15 epochs. So each epoch trains on the entire data set one time. So have to train on the entire data set 15 times in total. So we won't have enough time. So let's just ignore this step. And since I've already run it earlier, you can see that if you use this data set and you train it, you'll get like 99% accuracy. So that's like pretty good, like very good. So yeah, that'll be it for today's demo.
Yeah, so I guess if you guys have questions, we'll stay on for like a couple minutes, but otherwise we'll end the meeting in a couple minutes.
Was my voice clear?
That was pretty clear.
Okay, cool.
I didn't notice anything at least. Yes, I assume you we're good. So I'm gonna end the meeting now.
Okay, bye.